Let's discuss a common question. Basically, I think we can discuss at the top itself. So here is a steam power plant cycle, which is given with a regenerative cycle. Okay, so regenerative cycle is that at some point in the turbine, some steam is removed and it is used again for heating, uh, the inlet to the boiler. Okay, so that the water enters at a higher temperature to the boiler. So that is open feed heating that is done uh, to basically to improve the efficiency. Yeah, because the whatever the enters at boiler will be at a higher temperature, and that's what and what takes place in a boiler is a constant pressure process, and so it's basically the exit of the boiler will also be at the higher pressure. So this is basically a regenerative cycle. I mean, the other way of saying it is whatever the heat that is required in the boiler, okay, that some portion of heat that is required to convert water into steam, some portion of heat is supplied by this steam which is removed from the turbine. So whatever the heat content that is there in the steam that is removed part way from the turbine is used to heat the water, so that it converts into steam, and or it gets heated up to so that some heat in the boiler can be reduced. So basically the thermal efficiency is increased. That is the purpose of regenerative cycle. So here let's say, let's just imagine that a unit kg is flowing, just for simple purpose. So let's say the y amount is removed, fraction of steam. So the y will be the fraction, obviously. Let's say y kg is removed, so the remaining 1 minus y will be flowing through this, and ultimately they will again combine and open. So what I can say is that in the open feed water heater, so where there is no additional heat supplied, right? Whatever is just the water that is used to heat. So y into, I can write it here, y into your H6 is the enthalpy content, the total heat content in the stream coming from this side, and the stream coming from this side is basically 1 minus y is the mass into your y2 into your H2, that is the enthalpy at point number 2. So 1 minus y, so mass, basically what we are doing is mass into the enthalpy, because these are all specific enthalpies. So mass into enthalpies will give you the total heat content, plus we are doing m dot at 6, we are doing m dot H6, and then we are doing at 2 m dot H2. That should be the enthalpy at point number 3, that is m3 H3. Because in this open feed water heater, what you are doing is you are just heating up the water which is coming from 2, right? The water that is coming from 2 you are mixing. So it's just a mixing kind of a thing where there is no heat exchange with the surroundings, there is no work done. So enthalpies at the sum of the enthalpies at the inlet will be equal to the sum of the enthalpy at the outlet. So enthalpy at the inlet is yH6 into 1 minus y into H2. So basically mass into enthalpy. There is total enthalpy at the inlet of open feed water heater, and the outlet is the mass, which is 1 kg, because y plus 1 minus y is 1 into H3. So we know the enthalpies, so we can find out y. So y will be basically, if I have to write, y will be H3 minus H2 by your H6 minus H2. That is the equation. So H3 is what? H3 is 798.33 minus H2 is your 193.01 by, I am doing it here because it will be easy for you to analyze in the figure. H6 is 2860.2 minus H2, which is 193.01. So if we calculate this, basically H3 minus H2 by H6 minus H2, you get a close to 0.22. So 0.2270 is the fraction of the steam that has to be attached. So it's just the energy balance for open feed water. What you are doing is enthalpy at the inlet of, okay. So whatever you are getting from point 1 and 2 after condensation, it's basically a saturated water that is heated up by the steam that is coming from the turbine pathway. So it's just open mixing heating, okay, heat transfer through mixing, and 3 is just the thing. So we have just done the energy balance for the open feed water heater. So 0.2270 is the answer. Thank you.